In this section, we'll be looking at how to use COMSOL to check the corrosion and the deposit for a cathode and a anode material. So we'll draw our geometry indicating with both anode and cathode, we use this geometry, one side to represent the anode and another side to represent the cathode. And we are going to illustrate how the stress corrosion cracking will occur under the geometry. So at the end, we should be able to plot the local current density over a period of time, and also we should also see the stress corrosion cracking results for this model. So kindly follow to the end, and if there are any questions, please let me know. And please don't forget to subscribe and like the video for me. Thank you. When we move to our model wizard, we then select our space dimension, which will be 2D. Go ahead to electrochemistry, where we want to select corrosion secondary. So we go to corrosion deformed geometry, then we select secondary, corrosion secondary to our work. So we want to add this physics to our work. This will be using a secondary current distribution. Move to our steady, where we choose a time dependent with initialization, which brings us to our interface. So quickly go to our geometry where we add a rectangle. We want to add a rectangle, and we want to draw our rectangle. 0, 1. Same here. We want to choose the position as minus 0.01. Then we go ahead to build our geometry. We go on to add another rectangle to our work, where we also make here 0.01. Our height should be this plus a little change. We want to add a little change to our work. So 1, -4. So we just want to make a little change to the height, and also to the position as well. We want to make a little change to the position as well, which we go on to build selected, as you can see. So we have built our geometry. Go ahead to Booleans, and we want to make a union out of this. So we select both. We uncheck this. So we want to join these two to make it one. Those selected, and they are joined together, as you can see in here. So we can see that we've joined our two rectangles together to form single unit. We can load our parameters from our work. We load parameters from file. We'll be using galvanic corrosion. Using galvanic corrosion. I'd like to search for galvanic. So these are parameters. We found it. That's galvanic corrosion with deformation, as you can see. We load our parameters. So after forming our geometry, we go on to add an electrode surface to our work. So we add an electrode surface where we select where this electrode surface will be. So we select 2 and 4 for our electrode surface. We check the species conservation. Check that. Let's open to check all these sections. Okay. Then we can now go to the electrode reaction. So temperature from the model inputs, the equilibrium potential, we put in this expression. That's also our kinetic expression. We want to use a cathodic Tafel equation where we change our I naught exchange current density to this. We change our anodic current density to this. We move forward. And we go on to add a second electrode surface. So the second electrode surface will be here. And go to the dissolving species where we add a barrier. We want to name this as Mg. Then this is rho Mg. Go M Mg. So that's what we change in here. After we go to the electrode reaction, where we number of participating electrons, we make it 2. We set this to be 1. We set the equilibrium potential to be this. kinetic expression is made of the anodic tuffle, which will be IO underscore, and this is anodic, which will be N as shown. Add a limiting current density, which we'll define as ILIM, anodic, as shown, as we've done in here. So that's for the electrode reaction. So we want to check what we did earlier. I want to cross check and see if actually named everything as supposed to be. Our electrolytes itself, we go to electrolyte conductivity, where we make this user defined, and this has to be sigma as shown. Go to our multiphysics deformed geometry, check. Deformed geometry. So things set in here. Geometry, deformation also sets. Move to the non-deforming boundary. For the initial, go to the second. We want to select only 5. So we want to select only 5 for this. So we want to select only 5 for the deforming electrode surface, and we want to, for the non-deforming boundary, will be the rest as shown here. So we go on to check insulation. Everything sets, then we can proceed to check our time that we want to set. We want to set our time from 0 to 12 times 3600, and we want to end at 3 times 24 3600 as shown. This could be very clear for us. So we can go ahead and compute our work. Which generates our results as shown in here. So we've been able to generate our results as shown in here. We want to add a 1D plot group. 1D plot group to our work. Which we want to add a line graph. In our 1D plot group. So we want to select the data set from our steady solution 1. We want it from the remeshed. We want to select, as we've selected our solution, steady solution 1. So view our solver. We check our meshed. Okay. So actually, we wanted to, in our time dependent, wanted to make the steady extension an automatic remeshing. So I have actually gone there to do automatic remeshing and want to compute it again so that we can get that result because we need a remeshed solution. So I'm recomputing it so that we can get our remeshed solution. Because it's very important for our work. I just went to time dependent, came here. Okay, now, so we have our remeshed results. It's very important to allow us to plot our results. So now we have our remeshed solutions. Now we go to results, we add a 1D plot group and we add a line graph. Now we can add our steady remeshed solution. So that was exactly what's needed for our work. So our time selection, we want to select from the first our work. And we want to select here. We want to select from 2, 4, and 5 to 4, 5 as shown in here. We want to change our expression in here to CD.I log under ER1. That'll give us the local current density. If we should plot, this is what we have. We have in this plot. So I want us to close this space in here. Then our x-axis data wants us to change the parameter to an expression so that we can use an expression of x in here for our work. As you can see. To actually make it look this way. So we want to duplicate this work and we want to start from last. Let's plot and see. Okay. So from last, we've had our plots. We want to plot our work. So let's go ahead to open a file for this galvanic corrosion with deformation, which will open and add. We want to view as we have seen over here. So we go to want to add physics. We want to add physics to our work, new physics to our work. So we go and we add new physics to our work in here. So our physics, we come to chemical species transport. We go to transport of diluted species. Add to our work. Where we define the variables. We want this to be 2, we want our concentration to be CmG. We want this to be COH, as done in here. We want to add a moving interface. That's under mathematics. We add level sets. To our work. Go to the parameters. And we want to load from file. We want to load our parameters from file, which will be under deposit corrosion parameters. We've actually added these parameters to this. Our definitions, we want to add a step to our work. Smoothing, we want our size of transition to be this. So we want to add variables which will actually load from file. We want under deposit corrosion variables. This is not defined, but later will be defined. Later be defined as we move on the course of our work. Definitions, we want to add non-couplings and general extrusion as shown in here. We want to select, we want to select a boundary for that. So select boundary. Our source frame, we want it to be this way. We want to use source map. We go to advanced and we want to set the tolerance to the closest point as much as possible. Now, general extrusion. Go to our transport of diluted species. We want to uncheck this convection. We want to make it migration. Move to transport properties. And we want to define the diffusion coefficient as dm on s dot bf2 plus dm e on s dot infl. And we want to also define okay, so this is one. Okay, now it's defined. The diffusion coefficient as well, DOH S dot VF2 plus DOH E LS V F1. The full stop before this. We want to change the electric potential as well. We want to define it as Q. The charge number, we want it to be 2 and -1. Initial values 2 as well. We want to make here C or H4. Sorry, this is 0. As shown here. We go on to want to add reactions. We select our domain and we define a reaction should be R as delta this also is R let's go OH it's not delta go to our transport diluted want to add concentration to our work we select boundaries and we define our species to be H0 as defined in here. go to transport, and we want to add, move to surface reactions, we want to add electrode surface coupling. Choose 2 and 4 for our electrode surface coupling. The reactions coefficient, we want to change this to local current density. For this, it has to be local current density. Number of participating electrons, we want 4. And so the section 2, we want it to be 4. Go on to add surface reactions, and we want to add another electrode surface coupling. So this is the second surface coupling that we're adding. We select 25, we go to the reactions. Same here, we choose the second region. The number we want to for this section, and we want to start from -1 in here. Close, go to the level sets. We want to look at the level sets model. Where we define the reinitialization parameter. It should be this max for as shown in here. We've defined our parameter for the reinitialization. This side, we also have to define the parameter for the controlling interface thickness. It should be LSHM. We set the velocity field to this value. Set this to this value. This expression. Move to the initial values, and we set it as the fluid 2. We want to add an inlet. The inlets we select 2, 4, and 5. And we go on to add, once we've added an inlet, we have to add an outlet. Very, very important. What's that audio? So we want to add an outlet. So after selecting our outlet, we need to select which area our outlet will be, because we've already chosen where our inlet will be. So we select our outlet, and the outlet will be the outer areas, will be from 3, 6, 7, and 1. That will be our outlet. Go to our secondary electrode. We want to define our electrolyte conductivity, add an expression to it. That will be LS dot BF2 F2 plus sigma F1 BF2 BF1 plus short linear. Go to our mesh. We want to add edit physics induced. For the first size, we want to make this calibrate for fluid dynamics, as we want to do for the first one. We want a finer one. For the second one, we want also extremely fine. We want fluid dynamics, extremely fine. Wow, work. So we move to our free triangle. We want to add, I think we have to add a size to this. Add a size to our free triangle. And there should be, I think, for a boundary. We select 2 to 5 for our boundary. Predefined should be extremely fine. Let's build and see how it looks like. So, seeing how it looks like for now. We move to 31. We want to uncheck certain areas like the deformed geometry. We want to uncheck this. We want to uncheck this. So we want to uncheck these two. And we want to compute. Get rid of this. It should take some little time to compute. So wait patiently for it to compute. a while. I also wait for it to compute to take some time. To take some time. We wait a while for this to compute. Take some time. We wait a while for it to compute. It's We wait for some time. It's actually taking a while. It's taking a lot of time. Really sorry about that. But we can't continue unless we're done computing. So I'll plead with you that we actually wait. I'm sure yours is not also done yet. So we're almost 50% through with the computing, still computing. Patiently wait. So wait, I think we're almost done. Almost done computing. Finally, we're done. That's great. We have our results now. Took about 9 minutes. So we click on electrolyte, look at the streamline, and we want to see the positioning. We want to do a separating distance of about, let's make it about 0.035. We want to also make the range. Okay, the range is 100. We want to plot, let's see. And here we have our results. We go on to the surface. To our work, we put an expression as 1 here. Then we select our coloring. We want it to be uniform. We want our coloring to be uniform. We want it to be gray as well. Go to the surface and we want to add a filter to our work. We want to name this filter as LS That's 2 type 1 greater than or equal to 0.5. That will be our filter. We want to plot our filter. So when we plot our filter, this is what we have. You can see our filter in it as shown. We want to add a 2D plot group. We want our data sets from our remeshed solution. We want our data set from our, we want to select our time from about, let's say the last time in here. This is what you want to select, and we want to go ahead and add a surface to our 2D. We want to put this expression in here, and we'll go ahead and plot. This is what we have. We go ahead and add contour to our work. Contour to, we want to change the expression in here to s dot vf1. Unit should be 1. Labels should be, we have entry, or then we have labels, total levels. So let's make our entry mode levels, and want this to be 0.5 as shown. Let's change our color table to different color. Let's say uniform. Make it black in here. And plot. So that brings us to the end of this work, and I hope we're able to plot our work, able to follow till the end. Thank you. And please kindly subscribe if you haven't. And if you have any questions, please kindly drop them in the comment sections. And don't forget to like the video. Thanks. So we start by going to our model wizard, select new, and we select our space dimension, work with the 3D, which we select. Then we come here to select our physics. So we're actually going to use a secondary current distribution for our work. So we go ahead in here, when we choose under electrochemistry, we have primary and secondary current distribution. We have tertiary current distribution. So we go just under primary and secondary current distribution, we select the secondary current distribution. Then we go ahead to add this. Then we move to our steady, where we have to select our steady. And we'll be dealing with the time-dependent steady. So we go ahead to choose time-dependent with initialization. which we add. So this brings us to our interface, our COMSOL interface, where we have added selected our physics and our study. So we go ahead to add our parameters. We want to reload from file, programs file, COMSOL, multiphysics, applications. Then I think we can search decorative plating parameters. So when we search for decorative, it will quickly search for our parameters. Then we load it, we open, we add to our file, as you can see in here. So we've been able to load our file quickly, as shown over here. So I think we can start to build our geometry. We go to geometry, right click, then move to insert sequence, which we go ahead to add. And for our sequence, we'll be using the decorative plating geometry for our sequence. So this is our sequence that we'll be using for our work. So choosing decorative plating geometry sequence, we open, load. Okay, so now we have been able to load our sequence. Then we go ahead to build all. So that builds our geometry as shown in here. Want to show transparency as well. So as you can see in here, we go to materials. Check for materials also. We'll add our materials later, not now. So you go to secondary current distribution and you want to change the current distribution type. We maintain it as secondary for now. We'll be making some changes as well at the electrolytes. Also, we want to change the electrolyte conductivity to user defined, where we want to set this to K PPA. Here, as shown. So we want to go back to secondary current distribution. We want to add an electrode surface where we'll add to our work. So after adding your electrode surface, you go ahead to choose the domain. So we want to select domain 4. This where we selected to be our electrode surface in here. So as you can see, there are many sections. And we have the film resistance. Now we move down to boundary condition. We have the perturbation amplitude. We have the external electric potential. We have different expressions that we can actually change them to for the boundary conditions. We have average current density, total current, and many others that we can actually change. So we are maintaining it to be the electric potential. Now for dissolving depositing species, we want to add. So we go ahead and select this area. This is where we're able to add our species. So click on to add, and it has added a species to it. So we have S1 being density as this and molar mass as this. So we've added our dissolving depositing species to the electrode surface in here of our work. So like I said earlier on, we selected domain 4 for our electrode surface in here, and we went ahead to add the species, but we want to modify the variable for our species. We want to define it based on our parameters. So we go ahead to define this as Ni. We want it to be the Ro, Rho, Ni. We want this to be molar mass of Ni as shown. So we go ahead to open the subdivision for electrode surface, then we go on to check the number of participating electrons, stoichiometric coefficient for dissolving depositing species as well. We've seen that what we change when we change the variable over there, it has been defined over here. We want to change the number of participating electrons to 2. We want to change this side to 1 as well. And this is the equation that comes to solve it with. Goes down. Then the equilibrium potential changes to this Q and the Ni. Then move on to the electrode kinetics, where we want to choose, before that, we want to choose the local current density. So we go to electrode kinetics, then we select our expression type to Butler-Palmer equation and change this current density to this underscore nickel I Ni, non-nickel Ni. So we've changed the current density this side. And move ahead to duplicate this electrode surface. We have a second. Move to the electrode reaction where we compare, but before that, it has to be changed. The domain has to be changed. It has to be changed to this. That's for the second surface, and also the phase has to also change to average as shown over here. And this expression too has to change to this. As shown in here. Then move back to here and also the coefficient has to change to 1, has to be 1. So we go ahead to the electrode surface and we want to add a reaction. We've added a reaction. We've added a reaction to this. Okay. So move ahead to the reaction. Then we want to move to the number of participating electrons. We will move to the potential. We also move to the kinetics. We change to cathodic. Current density has to change to this. Change this section to this. Then we go ahead to the mesh. As shown. So we want to change the element size to a final. We want to build all. Be able to build. Go to our time dependence, our current distribution initialization. And we want to change this current to secondary. Then our time dependent, we want to change the output times. Let's change just this section, 60 and 600. Then we go ahead to, we can study now, compute. So we've been able to compute and we move to our results. So we move to the selection. We want to select just a particular area, which will be the boundary. We want to select this. want to plot to see. So that gives us the thickness change. Want to rename this plot to the posited thickness cathode. We want to duplicate this. We want to rename as the current efficiency cathode. We renamed it. We want to look at the surface and also change the expression in here to CD ILOC underscore ER1 CD.ITOT. As shown. So we've changed the expression in here. Then finally plot final work as shown. So that gives us our plots for our work.